Humble sand. This is what the building blocks of the future are made of. But making them is a long process comprising a great many steps. First, the silicon dioxide in the sand has to be converted into pure silicon. After that, it is cut into wafer-thin discs. In Dresden, these raw wafers are 300 millimeters in diameter and less than a millimeter thick. In our clean room, up to 35,000 chips are then made from each of these discs. In numerous process stages, the wafers are given their characteristic surface structure. After coating with a photoresist layer, the wafer surface is exposed, developed, and etched. This results in the desired conductor structure. Such structures are hundreds of times finer than a human hair. Dopants are then implanted in the material to increase the electrical connectivity of parts of the semiconductor. In subsequent phases, this and other process steps are repeated until the entire layout of the chip has been deposited on the wafer. This involves heating the wafer to more than 1100 degrees Celsius, in some cases up to 27 times. Up to 200 measurements are done, and up to 26 exposures. All in all, this can mean as many as 700 processing steps and 14 weeks processing time. Once this is completed, the microchip is assembled from as many as 30 such layers, like a mini skyscraper. Each layer has its own function. Interconnecting them makes the microchip highly complex. Semiconductor chips, the building blocks of our future.
This microchip can take up to 26 weeks to make. In its as many as 100 layers, billions of transistors are packed into an area about the size of a fingernail. They're the brains behind almost everything we use in our increasingly electronic world. Here's how these complex, tiny devices are made. The process begins with silicon-rich sand. Why silicon? Silicon is a semiconductor. It's the sweet spot between an insulator and a pure conductor. That means its properties such as its conductivity can be altered by adding impurities or doping to meet the needs of different electronic devices. This also allows us to control the electrical signals that pass through. Silicon is also abundant. It's one of the 10 most common elements found on Earth. But much of the silicon found in the wild is chemically bound to oxygen, so the two elements must be separated. The sand is combined with carbon and melted in crucibles to produce carbon monoxide and 99% pure silicon. After further processing, ultra-pure silicon is produced. Next, a seed crystal is placed in contact with molten silicon. As the seed crystal is slowly pulled away, silicon atoms are deposited on the bottom surface. The result is a large cylindrical boule, or a single crystal ingot of pure silicon. The boule is then thinly sliced into wafers. Silicon wafers typically have diameters of 1 to 12 inches, with the most state-of-the-art facilities being able to produce wafers up to 18 inches in diameter. Bigger wafers are, of course, able to yield more microchips. Once the silicon wafers are cut, the production process begins in full. Microchips are made in extremely sterile conditions, free from contaminants such as dust. If even just one particle of dust makes its way onto a silicon wafer, the entire batch is at risk of being ruined. This would derail a process that can take an average of 12 weeks. The first step of the production process is deposition. A thin, non-conducting layer of silicon dioxide is grown or deposited on the surface of the wafer. Then the silicon wafer is prepared for lithography by coating it with photosensitive and light-resistant materials. The next step is very critical: exposure. The prepared silicon wafers enter a lithography machine and are exposed to UV light passed through a reticle containing the chip's blueprint. The areas exposed to light are hardened, while unexposed areas are then etched away by hot gases to leave a three-dimensional microchip. The electrical conductivity of different parts of the chip can also be altered by doping them with chemicals under heat and pressure. This process can be repeated hundreds of times for the same chip, producing a more complex integrated circuit at each step. To create conducting paths between the components, a thin layer of metal, such as aluminum, is overlaid onto the chip, and the etching process is used to remove everything except the thin conducting pathways. Several layers of conductors separated by glass insulators can be laid down. Each chip on the wafer is then tested for performance before it's separated from other chips on the wafer by a saw. Since microchips are essentially circuits built on an incredibly small scale, they have a basic set of components. Capacitors can temporarily store an electrical charge. Resistors help control the electrical current. Transistors can either amplify or switch the electrical signals passing through. For more advanced chips, like those found on high-end graphics cards, there can be upwards of 28 billion transistors on board. More transistors on microchips allow them to send out more instructions, increasing the computational power. Moore's law predicts that computer chip manufacturing would advance at a steady rate, allowing transistor counts to double every 2 years. Based on the sheer power of the technology we use on a day-to-day basis, this decades-old prediction seems to still be mostly true. Manufacturers have been shrinking down their transistor sizes to fit more onto chips. Each breakthrough in transistor size has allowed the production of more powerful chips for our phones, computers, and gaming consoles. In recent years, they've gotten each transistor down to as small as 8 × 10 to the power of -8 inches in diameter, allowing an amazing 50 billion transistors to be crammed onto a single chip. Manufacturing microchips is truly one of our most complex feats, and yet innovations are happening every day.
The making of smartphones. Indeed, not just you and I have been using smartphones for quite some time, but the entire world. However, have you ever wondered how smartphones are actually made as a whole? From the idea concept to the final product result, the journey climbs a steep mountain. Watch the entire video to understand the whole process. When a company decides to make a new model, they already have an old model and a lot of previous research, so they don't have to start from scratch. Of course, I assume we already know this matter for a fact, but if not, you're just on the right video. All they have to do is fine-tune the old model through the feedback of users or experts in this area, while at the same time inserting new trends and technologies. All the shortcomings of the previous model are dealt with, and new innovations inject technology into the latter model. Step 1. Making of prototype. Ideas are devised in the boardroom after considering various options. Confirmation is passed to the R&D lab. The research team starts with a prototype where aesthetics must be considered first and is not really working. The model is passed on to stakeholders who can comment on making changes as needed. After the appearance of the model is zeroed, the internal working kit of the handset is processed. Then the reins of the vehicle are handed over to the electronics team. Therefore, it is here that the processor and memory and other specifications of the handset are determined. Next, a matching display screen and the required battery potential are selected. Of course, don't miss the front and rear cameras. The device is then armed with the selected components and checked for operational performance. After this, if the decision team is reasonably happy with the work, the handset will be handed to the top for approval. Fact check. Most of the world's smartphone manufacturing today is being done in China. Step 2. Software installation. The software team will now intervene to bring mobile phones to life. This is basically predetermined by the operating system loaded on the phone. The hardware that the electronic team plays is most important to be compatible for the smooth functioning of the operating system. To be precise, many experts use their own methods to verify that the system is working as expected. The selected design loaded with hardware and software is ready for mass production. At this point, it is often difficult to go back and modify the already approved working prototype. Step 3. Testing phase. Before production begins, the handset is rigorously tested for quality, performance and other parameters. They have been tested from both a hardware and software perspective. We carry out various tests such as drop tests, bending tests and water quality tests to confirm their performance. Step 4. Mass production. When the final prototype is ready, it's time for mass production. Internal components can be manufactured in-house or outsourced. In most cases, this information on new models launched by the company has been leaked to the public, and this can be both useful or not. It is convenient because it promotes scheduled release mobile phones, and this is a drawback because it gives critics the opportunity to spot the flaws in models that haven't been produced yet and drop their ratings. started mass production of quality pass models. This can be done at the manufacturer's own factory or outsourced to another manufacturer, also known as original equipment manufacturer, to manufacture according to the specified quality and standards. Smartphones are also assembled in this process. Foxconn is one of the leading manufacturers of devices on behalf of top companies such as Apple, Xiaomi, Nintendo, and Amazon. There are large manufacturing plants in many countries, the largest is in Shenzhen, China. Besides, if you ever wish to learn how to assemble and disassemble your iPhone and other smartphones, you can simply fulfill your wish by attending a mobile phone repair training conducted by the authorized company or an institution. Fact check. During mass production, smartphones usually are codenamed to avoid the leak of information related to specification and design. Step 5. Packaging. If the handset passes all the tests, it will be sent to the packaging. The handset is placed in a ready-to-ship box with accessories and user manuals. Mobile phones arrive at the store in stylish boxes or packages. It is usually manufactured from low-quality recycled cards with inserts made of vacuum-formed high-density polystyrene. It is a popular card because it is cheap and can be recycled. In addition, colors and images can be applied using a variety of printing techniques. Cards are usually lacquered to give the box a glossy or satin finish. Usually, the package is in the shape of a rectangular parallelepiped. This means that the space can be used to easily and efficiently transport and stack on shelves. Step 6. Shipment. The final stage of the entire process is shipping. These packaged phones are shipped to the distributors, suppliers, and retailers around the world, and it is the end customer who receives the mobile phone from these retailers. And that's it, guys. Hopefully after watching this video you understand how smartphones are crafted from the making of prototypes to the shipment process. Let us know which smartphone is your favorite in the comments section below. Also, if you like this video, give it a thumbs up and share it with your friends, and don't forget to subscribe to our channel for more informative videos. See you in the next video.
The first computers used to be the size of an entire room. Then they were built to fit on your desk. The newest design is a portable device that sits on your lap. And today's laptops are made even smaller and more powerful than ever. With its lightning-fast processor and impressive graphics, this laptop is designed for high-performance gaming. The computer's brain, called the motherboard, begins as a printed circuit board. Its pattern of lines and pads in copper is the wiring for the electronic components that will be soldered to the board. This machine places a stencil of the component layout onto the board and applies solder paste through the openings. A quality inspection camera photographs the solder paste and sends the images to a computer. The computer analyzes them, looking for any missing paste, misalignment, or other mistakes. If the board passes inspection, it passes through 15 robotic machines, each of which places up to 150 components on the correct locations on the board in just 30 seconds. Then the board runs through an oven that melts the solder paste, connecting the components to the board. Another camera inspection ensures that the internal processor is correctly soldered and that no component is missing or shifted out of position. After function testing and a visual inspection, the motherboard moves to the assembly line and is set aside for the time being. Next, technicians manually assemble the top half of the laptop, called the panel kit. They place protection film on the 15-inch LCD screen. Then they plug in the cable that will connect the LCD to the motherboard. They insert the LCD screen into a frame, with the web camera and microphone already embedded. Then they attach this antenna bottom cover to the screen cover and position the motherboard cable inside it. Next, they install the module for the webcam and microphone. They attach two hinges, which connect this panel kit to the rest of the laptop. Then they install the Wi-Fi antenna and the antenna bottom cover. All components are concealed in the antenna bottom cover behind this antenna top cover. They complete the panel kit by pressing in a thin metal frame around the screen. Next, they assemble the bottom half of the laptop. First, technicians attach the top cover to the panel kit hinges and the touchpad. Then they install the right and left speakers in the top cover. Now the motherboard comes back into play. After inspection, a computer-guided router cuts out openings to accommodate the computer's fans, which prevent the electronics from overheating. A gaming laptop generates a lot more heat than a regular laptop, and therefore requires two powerful fans rather than one. After checking that the fan screws are sufficiently tightened, they place the motherboard into the top cover. Contaminants such as dust or oil can impede proper contact, so as a precaution, they clean the connectors for the memory modules with solvent, then dry them with compressed air. Then they install the memory modules, the Wi-Fi and Bluetooth module, and the solid-state disk which stores data. They connect a high-capacity battery to the motherboard. Batteries for gaming laptops are typically larger because the faster processor and dual fans consume more power. The last component is the keyboard, which fits into a rectangular opening in the top cover of the bottom half. A laser etching machine marks the required information underneath. An automated machine tests numerous functions, and a quality control team tests several others, including the virtual reality feature. The LCD and keyboard color displays, and the keys. Not only must the keys function properly, they need to be durable, so enthusiastic gamers won't break them while playing.
An electronic circuit board is a computer component which can produce spectacularly realistic scenes. Animating this particular three-dimensional graphic took 4 months of work by artists and programmers with the aid of a G400 graphic processor by Matrox. A printed circuit board can be compared to a building composed of fiberglass floors, copper passageways, and stairs that link the floors between them. Cards are assembled with two technologies, surface wiring and wiring through the card. The components are placed into the holes and soldered into place. A stencil is used to apply soldering paste onto the card. This paste will solder the surface components. Here they place the stencil into the printing unit. It is through these holes that the soldering paste will run. The machine spreads the soldering paste, which contains, among other elements, a tin-lead alloy. The printing blades go into action. They spread the soldering paste on the stencil. This paste runs through the stencil holes and covers the metallic surfaces of the printed circuit board, which will establish the electric current. Here's the difference between an unprinted card and another printed one. The unprinted card surface is much more shiny. Now they're going to install the surface wiring elements. They are automatically positioned by this rapid placement machine. About 36,000 components are installed per hour, making it about 10 a second. This incredibly sophisticated machine is equipped with a viewing camera which verifies the alignment and dimensions of each part before installation. It unerringly positions the part at the exact spot. Another machine, slightly less precise than the previous one, installs parts where the space between two placement points is less than 0.5 millimeters. It can install 8,000 parts in 60 minutes. The card continues on its way toward the oven, which accomplishes an essential operation. Once the parts are secured, the card goes into a convection oven where the heat will solder the parts to the card. Different circuit connectors through the card are inserted into their respective holes. This operation requires great dexterity and is entirely done by hand. Then the metallic placement points need to be soldered to this card. The soldering of the circuit components through the card is done with a bath of molten tin-lead alloy at a temperature of 240 degrees centigrade. Now everything is installed. They have to do an initial electrical test. The card is placed on a bed of electrified pegs. These pegs make contact with the card's connecting points, allowing them to check for short circuits or open circuits in the card. And then a final test, a computer-aided operating test to see if the card is functioning perfectly. This company fabricates 200 models of different circuit boards and produces about 4,000 cards each week.
To capture light without distortion, multiple lenses must be combined and precisely aligned. To design a lens, Canon conducts tens of thousands of simulations involving everything from the type of materials used to the order and arrangement of lens components. Next, 3D computer-aided design is used to design the entire lens. Lens production begins with the polishing of each piece of glass. Essential know-how regarding polishing methods, polishing times, and polishing abrasives can only be gained through many years of trial and error. Lenses are polished thousands of times and then washed. Following careful inspection, the lens surface is coated to reduce reflection and protect against scratching. The finished lens is so precise that if enlarged to the size of the Tokyo Dome Stadium, the margin of error would be less than the thickness of a business card. Canon's polishing tools are made by master craftsmen with decades of experience. It's here that traditional craftsmanship meets leading-edge technology. Canon innovation is the history of the camera lens. Canon mass-produced fluorite, an ideal lens material. Introduced aspherical lenses. Achieved the first practical application of an ultrasonic motor, and developed optical image stabilization technology. Canon's breakthroughs in lens technology have redefined photography time and time again. In the ongoing pursuit of the ideal lens, Canon illuminates photography for future generations. The image sensor converts light entering through the lens into electrical signals. Canon applies its original technologies and know-how to develop high-precision image sensors that offer high-speed processing and low power consumption. Each pixel stores tens of thousands of electrons. This has made possible a digital revolution in astrophotography. Canon produces its image sensors in a clean room environment in which even a single speck of dust is unacceptable, and the sensors do not come into contact with outside air. Using a method similar to semiconductor chip production, micrometer order circuits are etched onto large disc-like silicon wafers. Each sensor is cut from the wafer. After bonding and other processes, the sensor unit is complete. Canon's entirely automated production process ensures that each delicate image sensor meets the strictest standards of quality. Canon has nurtured its sensor technology since the beginning, and now it's flourishing. How are digital cameras designed and developed? First, a designer sketches the body of the camera. A 3D model is then created on a computer and the details are worked out. The color and texture of the different parts and the camera's overall ease of use are then considered. The data is then passed on to the development team. Designing on a computer, the team incorporates various features and functions, striving to achieve a body design free of waste. Canon employs 3D computer-aided design to speed up the process by reducing the need for trial production and prototypes. After repeated verifications, a digital camera is developed. But before being commercialized, it undergoes rigorous testing. It's dropped over and over, and its buttons are pressed tens of thousands of times until Canon believes it has a finished product. Now the camera's ready for production. Various camera parts which have been developed and produced at different locations are transported to this factory for assembly. Efficient production requires the delivery of a precise number of parts several times every working day. Each delivery arrives just in time for assembly. The production process is centrally managed, and progress can be confirmed from anywhere in the factory, a system that supports the smooth supply of parts. The final stage in the production process is assembly. Canon uses the cell production system to assemble cameras into finished products. In the cell production system, assembly workers are grouped in cells, which can respond flexibly to the production demands of various global specifications. Digital SLR cameras are carefully assembled by cells inside a clean room. The superior quality of Canon digital cameras is made possible by the company's advanced technologies and production systems.